Welcome back. In this video, we're going to finish up our discussion of vectors in R2 by talking about the last operation we're going to study so far, which is called scalar vector multiplication. Recall, so far in R2, we have two operations on vectors. One of them was called the 2 norm, which we represent with a double vertical bars. And this goes from R2, the input, the thing that we put in is R2, and the output is a real number. So this is called the 2 norm. Also known as the magnitude. The second operation that we studied was called vector addition, and vector addition took in two vectors. So this little x right here represents kind of a placeholder. Right? On the left-hand side of this is going to be vector addition. So on the left-hand side of vector addition, we take a vector. On the right-hand side of vector addition, we take a vector. And then the output of this operation is a vector. This is called vector addition in R2. We now introduce a third operation called scalar vector multiplication. And this is going to use the same multiplication dot that we used before. On the left-hand side of the dot, we're going to have a scalar. On the right-hand side of the dot, we're going to have a vector. And when we multiply a scalar by a vector, we're going to produce another vector. So this thing right here is called the scalar vector multiplication dot. So scalar vector multiplication maps a scalar on the left, a vector on the right. Again, this is a placeholder. The nice thing about using an x is it doesn't matter what the name of the operation is, the pattern is the same. The x is kind of saying, hey, listen, the operation is going to go in between, and then on the left, this is the type of thing that's going to be on the left. On the right, this is the type of thing that's going to be on the right. The x says this is going to be a binary operation. Once we multiply a scalar by a vector, we're going to produce a vector. To this end, let's go ahead and define this. So let's let C be a scalar, and we'll let x be a 2 by 1 vector, and we'll have it be equal to x1, y1. Then we define C times x. So here we have C times x1, y1. So that's a scalar vector multiplication because we have a scalar on the left and a vector on the right. That's how you can tell that that dot is a scalar vector multiplication. And what we do there is we bring it inside each of the components. Notice this right here is a scalar multiplication. Right? And another way to write this is if you wanted to write it without the actual dot, you could write this as C, x1, C, y1. Okay? So let's look at an example. multiply c equals to 2 by x is 1, 1. Okay, so the solution of this thing, let's consider 2 times the vector x, which is 2 times 1 comma 1, which would be 2 times 1, 2 times 1, which of course is 2 comma 2. Okay, we can visualize this on the coordinate axis. Okay, so here's 1, 1, 2, 3, 2, 3. So let's go ahead. I should always label my axis if I'm drawing a graph. I think in a previous video I didn't do that. That's a sin. Always, always, always I should be labeling my graph. Okay. -1, -2, -3, -1, -2. So here we go. So here's the vector x. All right. When we take 2 times x, I knew that the vector x started at 0 because I wasn't told otherwise. If I'm not told otherwise, I can assume that the initial point of my vector is indeed the origin. Here's the vector 2 times x. So the vector x is here, and the vector 2 times x is here. And we might even look at, just for giggles, let's consider -1 times x, which would be -1 times 1 comma 1, which is -1 times 1, -1 times 1, which is just -1 comma -1. All right, so this would be this vector this way. Notice that if we write any vector as a scalar multiple of x, it's going to be along the same direction with different magnitude. So in other words, for vectors with initial point at the origin, 2 vectors are in the same direction if and only if one of the vectors can be written as a scalar multiple of the other vectors for some scalar. So for vectors, let's call them x and y with initial points at the origin, these 2 vectors are in the same direction. X is in the same direction of y, if and only if I can write x as c times y. Or another way is I could write y as 1 over c times x, or alpha times x. We're going to come back to this. Is a very, very important observation that's going to come back over and over and over again. If I had to choose a tattoo to get from this lesson, this might be the one I get tattooed on my bicep or tricep or somewhere cool. So when I'm going working out, I can feel really good about myself and my tattoos. Okay, so this is the idea of scalar vector multiplication. And I wanted to show you something. We haven't actually formally talked about vector subtraction. We also have vector subtraction. So if I take, let's say that I had x minus y, where I called x x1, y1, and y x2, y2. The reason that I didn't show you this was that this is actually just x plus negative 1 times y. So if you have vector addition and scalar multiplication, you get subtraction for free, because this would be x1, y1 plus negative 1 times x2, y2, which of course is x1, y1 plus negative x2, negative y2, which is x1 minus x2, y1 minus y2. When I add those two together, I get this third one, right? And you can look at vector subtraction as geometrically. So let's go ahead and do this. Let's look at an example. So maybe you have, so this would be 2, 1, and y is something like 1, negative 1. Okay, so x goes 2 out and 1 over, so there's the direction of x. And then y goes 1 out and 1 down. So now you have y. So here's x, and here's y. If we looked at x minus y, which we just said was the same thing as an x plus a minus y, well, minus y is going to be this vector here, right? Because it's going to be y flipped 1 unit in the other direction. Negative 1, 1. So then when I take x minus y, I'm going to produce a third vector which is going to be 2 minus 1, 1 plus 1, 1 comma 2. So I go 1 over and 2 up. And notice it's this vector right here. This is this vector. I go 1 over and 2 up. This vector starts at the origin. This vector starts at y. Right? Which makes sense. If I go y plus x minus y, so I go y plus x minus y, I should get back to x, which is exactly what I have there, right? So in general, the diagram for vector subtraction is if you have, here, let's call this x, and let's call this y, the vector going from y to x this way, this vector would be x minus y, because if I added y to x minus y, I go to y, x minus y, I get back to x. Similarly, if I go x, y, the vector going from x to y would be y minus x, right? Based on that same analysis. All of which is brought to you by a combination of scalar vector multiplication, vector-vector addition. Okay. All right, the last thing I want to say is, we say two vectors are equal if and only if they have identical components. the same magnitude and direction. Right? In this case, we write x equals y. Okay? Or another way to say this is x minus y equals 0. So these two are equal if and only if the components are equal. Another way to say this is that the length of the vector is 0. This is the 0 vector. It's the vector 0, 0. This is the 0 scalar because two norms are written like that. Right? So we say that two vectors are equal if and only if their components are equal, if and only if the difference of their components produces 0, if and only if the length of the vector is equal to 0. We'll talk more about where this comes into play later in the quarter. Okay, we've just wrapped up our discussion of the 3 operations so far in R2. In the next lesson, we're going to talk about R3, 3 dimensions. See you there.